Welcome to a journey of infinite exploration, a voyage through space and time that challenges the very limits of even our most vivid imaginations. Today, we will unveil the mysterious curtain of the vast cosmos to witness a genuine marvel of physics and astronomy, a structure so magnificent that it renders all our concepts of scale insignificant and fragile. We are speaking of what scientists call the largest structure in the universe, a colossal network of galaxies, galaxy clusters, and superclusters spanning a terrifying distance that light, the fastest entity in the universe, takes 15 billion years to traverse. Take a deep breath, for the story we are about to tell is not merely about dry numbers, but about the formation, existence, and profound significance of this grandeur regarding our place in the cosmic tableau. To understand this structure spanning 15 billion light-years, we must rewind time to the moment of genesis for everything, the Big Bang. Imagine, if you will, no space, no time, no matter, only a singularity of infinite heat and density. Then, approximately 13.8 billion years ago, an extraordinary explosive event occurred. Its sound, if one could call it sound, was surely an absolute silence torn apart by a violent expansion. In those first moments, the universe expanded at a dizzying speed, faster than the speed of light, a phenomenon known as cosmic inflation. Everything was unimaginably hot. But as the universe continued to cool, the first elementary particles began to form quarks, electrons, and subsequently protons and neutrons. About 388,000 years after the Big Bang, temperatures dropped sufficiently for electrons to combine with atomic nuclei to form the first neutral atoms, primarily hydrogen and helium. This was the moment the first light was released, a faint glow, a remnant that persists to this day as the cosmic microwave background radiation. This is the earliest snapshot of the universe, a blurry thermal blanket with extremely minute temperature fluctuations, merely a few millionths of a degree. It was those tiny fluctuations, those microscopic ripples on the surface of that primordial blanket, that served as the seeds for everything we see today, including the magnificent structure we are exploring. After neutral atoms formed, the universe entered a dark era where there were no stars and no galaxies. However, under the influence of gravity, regions of slightly denser matter in the background radiation began to attract surrounding material. Imagine invisible magnets slowly pulling tiny dust particles together in a vast room. This process continued slowly but relentlessly for billions of years. Giant clouds of hydrogen and helium gas began to collapse under their own gravity. When the mass was sufficient, pressure and temperature in the core soared, and then, ignition. The first stars blazed into life, bringing the first light to the dark universe. These stars, massive and short-lived, synthesized heavier elements, and when they died in spectacular supernova explosions, they scattered these elements into space, providing building materials for the next generation of stars and planets. Billions of stars congregated into larger units, galaxies. Galaxies do not exist in isolation. They interact, collide, and merge. They form small galaxy groups, then larger galaxy clusters. And then, we reach the next level of organization, superclusters. Superclusters are the largest collections of galaxies we can identify. Visualize a giant bunch of grapes, where each grape is a galaxy cluster, and each cluster contains thousands of individual galaxies. But even these superclusters are not the limit of organization. In the late 20th and early 21st centuries, with the advent of more powerful telescopes, particularly large-scale redshift surveys, astronomers began to map the universe in 3 dimensions with unprecedented detail. They did not just see galaxies, they measured their distances by analyzing the redshift of light, the Doppler effect showing that the universe is expanding and galaxies are moving away from each other. And then, they found it. Not a single object, but a massive web-like structure, stretching out and linking everything together. Scientists call it the cosmic web. The largest structure identified within this web, sometimes referred to by media with impressive names like the Great Wall or the Giant Filament, is an arrangement of superclusters, galactic walls, and filaments linking them together. The scale is astonishing. Scientists have identified structures with estimated lengths of up to 15 billion light-years. To visualize this figure, remember that the age of the universe is only about 13.8 billion years. This implies that this structure extends almost from the time of the Big Bang to nearly the present, or it encompasses a vast portion of our observable range. Let us pause to appreciate the magnitude of this number. 1 light-year is approximately 9.46 trillion kilometers. 15 billion light-years is a figure that the human brain cannot process by intuition alone. If we could fly at the speed of light, we would still take 15 billion years to travel its length. That is a number with 16 zeros. This structure is not a solid block. It resembles a giant sponge, or a complex spider web woven in space. Most of the space is comprised of nearly empty voids where there is very little matter. Galaxies and galaxy clusters concentrate along delicate filaments and flat walls where superclusters congregate. This 15 billion light-year structure is the combination of a series of walls and connecting filaments on the most macroscopic scale. How do scientists know this terrible size without going there? The secret lies in measuring distance through light. When we look at distant galaxies, light from them has traveled billions of years to reach our eyes. During that journey, the universe has ceaselessly expanded. This expansion stretches the wavelength of light, shifting it toward the red end of the spectrum known as redshift. Every galaxy we observe has a different redshift. The greater the redshift, the farther the galaxy is from us, and consequently, the longer its light has taken to reach Earth. Astronomers use massive telescopes, such as the Sloan Digital Sky Survey or other deep survey projects, to collect the spectra of millions of galaxies. They precisely measure this redshift, then apply the standard lambda cold dark matter cosmological model to convert the redshift value into actual distance in three-dimensional space. Imagine standing in a dark room and trying to reconstruct its layout simply by turning on a flashlight and watching the light reflect off distant objects. Astronomers do the same on a cosmic scale. They create giant three-dimensional maps of galaxies. When these maps are synthesized, the image that emerges is not a random distribution of galaxies. Instead, they form a complex web structure where superclusters form dense nodes connected by filaments of matter stretching hundreds of millions of light years. The largest structure they found, a synthesis of many walls and connecting filaments, reached the staggering size of 15 billion light years. During the exploration process, specific structures have been named and studied thoroughly, testifying to the scale of the cosmic web. The Hercules Corona Borealis Great Wall. This is one of the most frequently mentioned candidates when discussing large structures. It is a super-dense wall or filament of quasars and galaxy clusters. Initial estimates suggested its length could reach about 10 billion light-years, but as researchers integrated more data from neighboring regions, its connectivity and extension suggested a continuous network much larger, pushing the overall scale near the 15 billion light-year mark when including the neighboring structures with which it interacts strongly. The Sloan Great Wall and the Sloan Great Wall Extension. Before larger structures were defined, the Sloan Great Wall, discovered in the year 2002, was the largest structure known, with a length of about 500 million light-years. However, later studies showed it is merely part of a much larger network. As scientists expanded the survey range, they realized the Sloan Great Wall was a knot in a much longer system of filaments. Adding to this ever-growing picture of cosmic gigantism, astronomers in late 2023 announced the discovery of Hulelana, a massive bubble of galaxies 1 billion light-years wide. Located in the constellation Boötes, this spherical shell is a fossilized acoustic wave from the early universe, known as a baryon acoustic oscillation. Remarkably, the Hulelana bubble incorporates other known massive structures, including the Sloan Great Wall and the Boötes supercluster, into its shell, proving that what we once thought were isolated great walls are actually edges of even vaster cosmic bubbles. Furthermore, in early 2024, a team led by astronomers from the University of Central Lancashire unveiled yet another colossal find, the Big Ring. This almost perfect ring-shaped structure has a diameter of 1.3 billion light-years and a circumference of 4 billion light-years. It sits in the same neighborhood as the giant arc, a crescent of galaxies spanning 3.3 billion light-years that was discovered by the same team in 2021. The existence of the Big Ring and the giant arc in such close proximity suggests they may be part of a single, even larger cosmological system. The structure spanning 15 billion light-years that we are discussing is not a single entity defined once and for all. It is the aggregate of the connection between the largest superclusters, forming a seamless web stretching almost across the entire radius of the observable universe. It shows that matter in the universe is not distributed evenly but is arranged in a form resembling a giant sponge. Why is a structure extending 15 billion light-years important? It is not just a physical record. It touches upon the nature of existence and the evolution of the universe. When scientists found structures larger than 1 billion light-years, they began to encounter a theoretical problem, the cosmological principle. This principle states that when viewed at a sufficiently large scale, the universe must be homogeneous and isotropic. This means that no matter which direction you look, you will see the same average matter density, with no center and no edge. However, a structure extending 15 billion light-years, along with the newly discovered giant arc and big ring, seems to challenge this directly. If the universe is homogeneous at a large scale, why is there a filament so large? Is it proof that the universe is not homogeneous at this scale, or is it evidence that our understanding of dark matter and dark energy needs adjustment? Most current studies conclude that although this structure is massive, the universe is still considered homogeneous at even larger scales, perhaps over 200 billion light-years. The 15 billion light-year structure, though extraordinary, may just be part of density fluctuations in a much larger universe where the distribution of matter eventually becomes smooth. Visualize this: we live on a tiny planet, orbiting a tiny star, in a tiny galaxy, the Milky Way, located in a supercluster, the Laniakea supercluster. And our Laniakea supercluster is just a tiny speck of dust, located somewhere on a filament hundreds of millions of light-years long, and this filament is part of a giant web that may extend up to 15 billion light-years. The feeling upon realizing this is a combination of deep humility and intense excitement. We are not the center, but we are part of a system organized with magnificent order. These great structures could not form solely from the ordinary matter we see: stars, gas, dust. The mass of all visible matter is insufficient to generate the gravitational force needed to pull everything together so quickly in cosmic history. The solution lies in the invisible components that make up the majority of the universe's mass: dark matter. Dark matter does not emit, absorb, or reflect light. We only know of its existence through its gravitational influence on ordinary matter. In the primordial stages of the universe, dark matter, unaffected by radiation, began to create deeper gravitational wells. These wells attracted hydrogen and helium gas, forming invisible frameworks. This giant cosmic web structure 15 billion light-years long is the imprint of dark matter. It is the skeleton upon which galaxies and galaxy clusters are pinned. The most advanced computer simulations, using the laws of physics and estimated amounts of dark matter, have recreated the formation of the cosmic web with astonishing accuracy. When they run the simulation, filaments, voids, and the largest galaxy clusters appear exactly like what we observe through telescopes. However, another factor governs the fate of this structure: dark energy. If dark matter is pulling everything together to form structures, dark energy is pushing everything apart, causing the universe to expand increasingly faster. Dark energy acts as an anti-gravity force, inflating the universe. In dense regions like superclusters, the gravity of dark matter and ordinary matter is still strong enough to hold them together. But at larger scales, especially in the voids and between filaments, the expansion caused by dark energy is winning. This means that this massive structure spanning 15 billion light-years, though currently existing, will be stretched further apart over time. The connecting filaments will thin out, and galaxy clusters will be isolated from each other by the ceaseless expansion of space. Let us try once more to visualize the journey of light. When we look at this largest structure, we are looking into the past. The nearest part of this structure may be only a few hundred million light-years away, where light has just reached us. But the farthest parts, contributing to the total length of 15 billion light-years, have light that began its journey from the very early epochs of the universe, when the cosmos was just an infant. Imagine standing at one end of this giant filament. You see billions of galaxies scattered along it. You are seeing light emitted when the galaxies at the other end of that filament were still in the stage of forming their first stars. It is a dimension of time that our minds struggle to grasp. This structure is a living fossil, recording the history of the universe's formation on the largest possible scale. It is proof of the evolution from a state of near-perfect homogeneity after the Big Bang to a universe full of complex structures, arranged in a magnificent gravitational order. Identifying and mapping this structure is not the end of the quest, it opens deeper new questions. Today's observational tools, such as the James Webb Space Telescope, are helping us look deeper into the past and observe younger galaxies. This telescope has the ability to pierce through cosmic dust clouds and see extremely high redshift light, helping us identify filaments and matter knots in even earlier eras. Looking to the immediate future, the Euclid Space Telescope, launched by the European Space Agency in July 2023, has begun its mission to map the geometry of the dark universe. Euclid will create the largest and most accurate three-dimensional map of the universe ever produced, observing billions of galaxies out to 10 billion light-years. This dark universe detective aims to reveal exactly how dark energy and dark matter have dictated the formation of these massive webs over cosmic time. Will the cosmic web continue to extend at scales we have never seen? Next-generation projects on the ground and in space will continue to collect redshift data from tens of millions of galaxies, creating increasingly detailed and accurate three-dimensional maps. The goal is not just to measure the largest size but to understand why matter organized itself in this pattern. Technical details still open include: 1. Dark matter density. We need to know the exact ratio of dark matter to ordinary matter to confirm structure formation models. 2. Influence of supermassive black holes. How do supermassive black holes at the centers of large galaxies influence the distribution of matter in superclusters? They may accelerate star formation or push matter out, impacting the shape of filaments. 3. Reaction to dark energy. As the universe continues to expand faster, how will these structures disintegrate? Will superclusters be completely isolated, leaving islands of galaxies in an ocean of expanding space? Let us return to emotion. When we face the number 15 billion light-years, the first feeling is often overwhelming awe and fear before the infinite. But think of it another way: we, living creatures on a tiny speck of dust in a remote corner of the Milky Way, have developed the intellect not only to recognize the existence of these structures but also to have the capacity to measure and model them. That is an extraordinary triumph of the human mind. We have gone from merely seeing spots of light in the night sky to sketching the map of the universe on the largest possible scale, traversing nearly the entire visible history of time. The largest structure in the universe, stretching 15 billion light-years, is not just an achievement of astrophysics, it is a powerful reminder of the connectivity of all things. Each galaxy in that structure, though separated by billions of light-years, was born from the same single event, the Big Bang, and was woven from the same material of dark matter and ordinary matter and the same set of fundamental physical laws. When you look up at the night sky, remember that even if invisible, the unseen filaments of dark matter are pulling and shaping superclusters into a network spanning 15 billion light-years. We are not alone in the void, we are part of a grand design, a cosmic work of art created from gravity, time, and ceaseless expansion. That is the story of the largest structure we know, a giant thread of existence, a testament to the majesty of the universe we are fortunate to explore. And this journey of understanding, I am certain, will continue to lead us to surprises even greater than this in the future.